So we're going to start with our notes on page 116 on math induction. Math induction is a method to prove statements that involve natural numbers. We're going to prove that these statements are true for all natural numbers. We're going to have a three-step process that I will refer to as V1, sit, and pit. V1 is when we verify that it's true for n is equal to 1. Sit is when we say it's true when n is equal to k. And pit is when we prove it's true when n is equal to k plus 1. And after we have done these three steps, then we can say that the statement is true for all natural numbers. So the best way to do this is to actually jump into some examples. So on the page 116, after we talk about the definition of math induction and the three-step process, make sure that you tape in the examples that we're going to do in the next pages. So these are 8 examples. We're going to see if we can do 2 or 3 of them in the next few pages to see if you can get the hang of them. My suggestion is to also take a look at the other ones we don't do and see if you can prove those. So on page 117, we're going to start off with example number 1, which our job is to show that 1 plus 3 plus 5 plus however many numbers we want will equal to n squared for all values of n. So the very first thing we're going to do is going to be V1. That's when we verify that it's true when n is equal to 1. So I want you to notice that this part right here is what we call our general term. So I'm going to plug in n is equal to 1 there. So I have 2 times 1 minus 1, and that equals to 1. And I want to see if it's true for 1 squared. And in our case, it is true. So we have completed for sit. Remember, we're going to let n equal to k, and we're just going to say it's true. In other words, we're going to say that the sum, 1 plus 3 plus 5 plus however many, plus 2n, in our case k, 2k minus 1 is equal to k squared. So there, we just said it. So we've finished the second step. The third step is where we have to prove that it is true for n is equal to k plus 1. So I'm just going to do substitution. So what I'm going to show that we want to prove is that 1 plus 3 plus 5 plus all of these plus the 2k minus 1 plus then the next one, because I'm going to let n equal to k plus 1, which is 2k plus 1 minus 1, and we want to see if that is true for k plus 1 squared. So we can see that this part, we already know the sum of all of these. This is k squared. We know that because we said it was true in the sit portion. Alright, so now we need to figure out what does this part look like. Well, using the distributive property, I get 2k plus 2, that's this part right here, minus 1, so I get a positive 2k plus 1. And the question is that still the same thing as k plus 1 squared? Well, the next thing we're going to do is we're going to factor this side, and we're going to find that this is indeed k times k, and then 1 and 1, and then plus and plus, which is the same thing as k plus 1 squared. So because of this, we know that it is true for all values, because we knew it was true for n is equal to 1, we knew it was true when n was equal to k, and we have figured it out. It works for even k plus 1, the next term. So this guy is true. Let's try example number 2. For example number 2, our job is to show that 2 to the nth power is greater than n for all n. So again, we're going to start off with V1. Remember, V1 is when we let n equal to 1, and we got to make sure it's true. So 2 to the 1 is greater than 1. That is true. 2 is greater than 1, so we're okay with that. That is true. The next thing we need to do is say it's true. So we're going to let n is equal to k, and we're going to say 2 to the k is greater than k. Done. We've said that. The third one is where we have to prove that it's true for n is equal to k plus 1. So in other words, I'm going to have 2 to the k plus 1, and we got to show that that is greater than k plus 1. All right, so let's start off with what we do know. We do know that 2 to the k is greater than k. We know that because we said it was true in step 2. So what if I multiply times 2 to both sides? My inequality stays the same because I didn't multiply by a negative. Remember, I'm multiplying by 2 to the 1 power. And that's special because this is the same thing as 2 to the k plus 1. On this side, we have that this is 2 times k, or k plus k. So the question is this greater than k plus 1? Well, the answer is yes, because k plus k is going to be bigger than k plus 1, because remember we said that k was greater than 1 from the very beginning. In our rules that we said that sit means k is greater than 1, so therefore this is going to be true. So we have proved it for n is equal to 1. We said it was true for n is equal to k, and then we just finished proving that it's true for n is equal to k plus 1.